Let's continue. All right, let's look at another example. A constant force of 50 newtons acting on the body initially at rest gives an acceleration of 0.1 meter per second squared for 4 seconds. Calculate the work done by the force. So another example on work done, calculate the work done by the force. So the first step is to write down what we are given from the question. We are given the force of 50 newtons acting on the body initially at rest. So a body at rest has initial velocity u for initial velocity equals 0. Remember from the equations of Newton's equations of uniformly accelerated motion. U stands for initial velocity, and at rest means it's starting from 0. Acceleration of 0.1 meter per second squared for time of 4 seconds. So we write down what we're given. So we have to calculate the work done. The distance s is obtained from, so we could use because to get the work done, remember work done is force times distance. So we're given the force, we need the distance. So to calculate the distance, we can use these other parameters which we are given, UAT. So I think UAT rhymes with the second equation of motion, S equals to UT plus half AT squared, where our U is 0, our T time is 4 seconds, half AT squared. Treat half AT squared together, half your AT squared times squared. So half of 0.1 is 0.5 times 4 squared 16. Treat this together, please. Remember your board mass, multiplication comes before addition. So simplify, you get 0.8. So we've gotten the distance now. So multiply the distance by the force to get the work done. So to obtain work done, force times distance, so that gives us 40 joules. So it's quite straightforward using Newton's equations of motion to get whatever is missing in the formula for work done, in this case distance. Okay, remember you also have to know that in a force displacement graph, the work done is equal to the area of the shape formed by the force displacement graph. So for instance, we have a question like this. So this is a force displacement graph. Okay, force axis by distance x. Okay, this x is a symbol for distance. Is being used as a symbol for distance for this particular question. See, unit of distance is meters, unit of force is Newton. So the area of the shape. Okay, so this is a force displacement graph. So the area of the shape, it could be a semicircle or it could be any other shape. To be the area of the semicircle gives us the work done. So work done can also be found from the area of a shape, the shape in the force displacement graph. Okay, so let's step up. We have a machine, an example, a machine of efficiency 80% is used to raise a body of mass 70 kg through a vertical height of 3 meters in 45 seconds. Calculate the power input. To calculate the power input, G, acceleration of the gravity, is given as 10 meters per second squared. All right, so we're given efficiency, we're given mass, we're given vertical height or vertical distance, and we're given time. Power, remember power is we've not talked about power, but power is there's a connection between power and efficiency, and that power, by the way, is the rate of work done, the rate of doing work. Power is the rate of doing work. Okay, so power is the rate of doing work. So it's basically power is equals to work done over time taken. Work done over time taken, and is the rate at which energy is expended. So in this case, potential energy, the rate at which it's expended, or the rate of doing work. And we also have a relationship between efficiency, power. So we have power output over power input times 100 gives us the efficiency of a machine. So these are some of the details we have to look into. So read the question again. A machine of efficiency 80% is used to raise a body of mass 70 kg through a vertical height of 3 meters in 45 seconds. Calculate the power input. So the efficiency, let's state down what you're given. Efficiency 80%, mass 70 kg for the body or object in question. The distance moved by the body is 3 meters. The time is 45 seconds. Okay, so it's a machine that moves. Okay, an object. All right, so the efficiency is given by power output over power input. The idea of efficiency is also relevant in machines. Okay, power output over power input times 100 over 1. Now the power output is the useful work. The power output is the part of the input power that the machine actually uses to do the work. So you can always get your power output from the details here. This is the mass, this is the height, okay, and this is acceleration due to gravity and over time. Remember, power can be gotten from mass times acceleration due to gravity times height over time. So the details always tells you what the machine does. So the power output is the useful work done by the machine. All over the power input, the power put into the machine. So power input, what goes into the machine. Power output, what comes out of the machine. The part of the input that the machine actually uses is the power output. So mgh is this the mass times acceleration of gravity g times height, the vertical height that the object is moved through over time, because we are talking about power now, not just work done or energy. Okay, so we have 46.67 watts. Unit of power is watts. Take note of that. Unit of power is watts. So power has its own units. It's in watt, measured in watts. Measured in watts. Okay. So energy and work done are, of course, they have related concepts and they have the same unit, joules. Now the power inputs can be made to stand alone, make the subject of the formula. Power input just comes here, efficiency comes down here. So power output over efficiency times 100. So the power output we've calculated from the details given in the question. This is what the machine does. Okay, the power output is what the machine actually does. It moves 70 kilograms through a vertical height of 3 meters in 45 seconds. Okay, this is your gravity. Okay, gravity it works against. Okay, so the power input from here, putting the power output times 100 over the efficiency. The efficiency is given the question as 80%. Okay, it's not an ideal machine, so we get 58.33 watts. If it was an ideal machine of 100%, if the efficiency was 100%, it would be an ideal machine. In that case, the power output would be exactly equals to the power input. But you see, there's a difference. So this difference between the power input and the power output is due to losses from friction, mostly from friction, okay, or heat losses. Okay, so that's why the most machines are not 100% efficient due to friction within the moving parts. Okay, so there's a loss of power or energy as the case may be. All right, so that is an example. So let's move on. We can get more examples. Let's look at some concepts related. In a real machine, efficiency is usually less than 100% because the work output is usually less than the work input because some energy is lost to friction. Okay. Also, the power input is equals to the amount of power supplied to a machine. Okay. The power input is equal to the amount of power supplied to a machine, and sometimes it could be gotten from the power rating of the machine, the power rating. So that's the power needed to be supplied to the machine, and then what comes out of it, the useful work. Okay, the useful part of the power, the part of the power supply that is used, the amount of power that comes out of a machine is known as the power output. The amount of power that comes out of a machine. Okay. Okay. So efficiency is equals to, as a fraction, is power output over power input. All right. Okay. So let's look at another example. We have other examples that we can look at. Let's look at this one. A ball. Example 7. A ball of mass 0.1 kilogram is thrown vertically upwards with a speed of 10 meters per second from the top of a tower 10 meters high. Neglecting air resistance, its total energy just before hitting the ground is what? A ball of mass 0.1 kilogram is thrown vertically upwards. So we have from the top of a tower. So let's look at this diagram.